Hi, welcome to the introduction of Quiqbox.jl, a flexible basis set generator for electronic structure problems. My name is Weishi Wang. I'm from the Department of Physics and Astronomy at Dartmouth College. Before I talk about Quiqbox, I would like to briefly introduce electronic structure problems, where its main application lies in. Electronic structure is the intersection of multiple disciplines such as quantum chemistry, quantum physics, and material science. The subject of electronic structure problems are the electrons in quantum many-body systems. Based on the Born-Eibelhammer approximation, we can separate the electronic Hamiltonian from the total Hamiltonians of the many-body system. One of the main goals of electronic structure study is solving the eigenvalue problem of the electronic Hamiltonian, especially the ground state problem. A generalized procedure of solving the electronic structure problem can be summarized as follows. Given an electronic Hamiltonian, one would need to perform a basis set discretization of the Hilbert space it lives in, and then one can apply a model approximation to simplify the problem, and finally apply an eigensolver to solve for the eigenstate. As we can see, the design of a basis set will actually affect the performance of the later on model approximation and eigensolver. So it would make sense to develop a systematic study or toolbox to provide tailored basis set design for different model approximation and eigensolver. This is why we started developing Quiqbox as a flexible basis set generator. Quiqbox is written in Julia because it's fast, dynamic, and composable. These core features of Julia also reflect on the design philosophy of Quiqbox. First, as a basis set constructor, Quiqbox is able to provide native and efficient analytical evaluation of one electron and two electron integrals. Secondly, the basis functions in Quiqbox are composite basis functions based on Gaussian-type orbitals. Normally, when Gaussian-type orbitals are used to form basis functions, multiple concentric Gaussian-type orbitals with different weights are summed up together to form a contracted Gaussian-type orbitals. And those contracted Gaussian-type orbitals are normally located on the position of nuclei. However, in Quiqbox, not only can you construct contracted Gaussian-type orbitals, but you can also construct basis functions that are combinations of multi-center Gaussian-type orbitals. Moreover, one can also lift the constraint of the center locations of the basis functions so that floating or fixed position basis functions are also available. Another unique feature of Quiqbox is that it allows basis function parameters as the mapping functions of more primitive variables. This means that not only the typical parameters of a contracted Gaussian-type orbital, such as contraction coefficients, center coordinates, and exponent coefficients can be the parameters of a basis set, but some more underlying variables can also be the parameters. These flexible options of basis functions constructions allows the user to use Quiqbox to build more customized basis sets. For example, a grid-based basis set where the basis functions are located on fixed grid points, or a set of more delocalized orbitals while still obeying certain geometric conditions. Second, as a basis set optimizer, Quiqbox provides restricted and unrestricted Hartree-Fock methods to approximate the ground state energy of the electronic Hamiltonian. And based on the Hartree-Fock approximation, it can provide variational optimization of the basis set parameters. Specifically, both symbolic differentiation and atomic differentiation are utilized. Symbolic differentiation is used to calculate the partial derivative with respect to typical parameters of contracted Gaussian-type orbitals. When these parameters are functions of primitive variables, automatic differentiation is applied. Thus, the optimization procedure of Quiqbox is both efficient and extensible. Specifically, instead of directly calculating the gradient with respect to the parameters, since symbolic differentiation is utilized, a temporary basis set is able to be constructed. And then the gradient with respect to the parameters of certain functional can be calculated. So in the future, instead of Hartree-Fock functional, we can replace it with other algorithms. To sum up, the hybrid differentiation technique provides a versatile and extensible differentiation engine for the variational optimization of basis sets in Quiqbox. At last, let's have a look at the working pipeline of Quiqbox. First, you need to define a molecule. Instead of constructing some proprietary structure, you only need to define two arrays. Next, you need to build the basis set around the molecule. You can do it in a more traditional way, where you directly group together the atomic basis sets of the nuclei inside of the molecular system. On the other hand, you can construct basis functions that are correlated to each other, so that the basis set formed by them will preserve the geometric symmetry of the molecule. You can also use basic linear operations to combine different basis functions together to form new ones. Then, to optimize the basis set, you can use the built-in function markParims to mark and extract all the parameters from the basis set. You can then optimize with respect to part of them or all of them. After the basis set is optimized, you can then run a Hartree-Fock method to get the Hartree-Fock approximation of the ground state. At last, you can also get the electronic Hamiltonian with respect to the new basis generated by the Hartree-Fock approximation using the optimized basis set. To sum up, the syntax of Quiqbox is aimed to be both simple and flexible. In the future, we would like to first support more electronic structure methods for basis set optimization, such as multi-configuration methods like coupled cluster. We also want to mention that we don't really want Quiqbox to be a heavy package that does all the work in electronic structure study. Instead, we want it to be a useful tool that can be easily incorporated with other packages, such as electronic structure packages and quantum computing packages. We're still working on more to realize that. Thank you for your time.